Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to today's webinar, Engineering Motor Intelligence for Electrification. My name is Megan Purdy and I'll be your host for today. In keeping with our custom, Engineers Australia acknowledges the traditional custodians of the countries throughout Australia and recognise their continuing connection to land, waters, skies and community. We recognise Aboriginal and Torres Strait Islander peoples as the oldest continuous cultures on Earth and our first engineers. We pay our respect to them and their cultures and to elders past and present. Before we get started, I'd like to acknowledge that today's webinar has been hosted with Engineers Australia's industry partner, Schneider Electric. Schneider Electric are leading the digital transformation of energy management and automation. From energy and sustainability consulting to optimizing the life cycle of your assets, they provide services to meet your needs. Schneider Electric technologies help you become more efficient, reduce costs, and meet your sustainability goals. Now, today we'll hear from our speakers, followed by our audience Q&A, so I encourage you to please send your questions through to our speakers via the chat box. I'd now like to welcome our speakers for today, starting with Hai-He Shin, Offer Manager, Motor Control and Universal Enclosures, Schneider Electric. Hai-He works on strategies to help customers improve efficiency and reliability through smart motor management solutions. Hai-He collaborates with global teams to bring practical solutions to market and supports engineers in adopting technologies that reduce downtime and optimize energy use. Our next speaker will be Cherise Tabner, Offer Manager for Soft Starters and Variable Speed Drives at Schneider Electric. Cherise's roles focuses on developing and executing marketing strategies for motor control and drive solutions, ensuring alignment with customer needs and industry trends. She works closely with sales teams, product managers, and global stakeholders to position Schneider Electric's drive offerings effectively in the market. Cherise is responsible for driving product awareness, supporting campaigns, and enabling growth through digital tools, training, and customer engagement initiatives, all while promoting energy efficiency and sustainability in motor control systems. And our final speaker will be Daniel Hancock, Senior Technical Sales Consultant at Schneider Electric. Daniel specializes in automation hardware, software, and integration, leveraging expertise in Fieldbus, PLCs, drives, and integration. Passionate about delivering tailored automation solutions, Daniel provides expert technical support and guidance to clients across various industries. Please join me to welcome Hai-He, Daniel, and Cherise.
Thank you for the introduction. So today's agenda will start off with an introduction to motor management, discussing the fundamentals and today's key challenges. We'll explore what sort of data is critical and the importance of connected products. We will discuss optimizing operational efficiency and creating sustainably designed systems, ensuring we incorporate the human element as well as the operational environment in our design. We'll have a case study showcasing the importance and benefits of intelligent motor management systems, and we'll end on what's next for you, as well as a Q&A. My name is Hai-He Shin. I am the Offer Manager for Motor Control and Universal Enclosures at Schneider Electric. Today I'll be joined by two panelists and fellow colleagues, Cherise Tabner, Offer Manager for Soft Starters and Variable Speed Drives, and Daniel Hancock, Senior Technical Sales Consultant. Let me walk you through a brief history of motors and motor management. So motor management has evolved over time alongside mainstream technological advancements we see in our day-to-day lives. Over 200 years ago, electromagnetism was discovered in the 1820s, a commonplace technology we see in our modern-day contactors. We had the introduction of AC motors in the 1880s, and the first contactor developed by Schneider Electric in the 1920s, just over a century ago. With the advancements in computer processing came the first set of commercially viable variable speed drives in the 1990s. we saw the rise of microcontrollers that make integrated motor management solutions with communications and diagnostics possible with a significantly smaller footprint than ever before. Today, our technology can compute real-time modeling, predictive maintenance, and advanced and intelligent motor control. So it's fascinating to see how far we've come in the last 2 centuries and where we look to go with the rise of automation and the need for reliability. What we see on the screen is a typical architecture commonly used for motor control. We have an isolator or a load break switch with a visible way to disconnect for safe maintenance, a circuit breaker for short circuit and cable protection, a mechanical contactor for switching on a motor on or off on command, and an overload relay for thermal protection. This is the baseline of motor control with components for protection and switching. What today's webinar will discuss is how do we take the fundamentals and enable the devices to work with each other cohesively and gather critical data of the motor's performance to get insights and actionable data. In a nutshell, we're turning motor control into a connected data-driven system that delivers real-time insights and actionable decisions. Based on the conversations we've had with key players in designing, installing, and running a motor management system, including design engineers, contractors, and end users, we've identified 3 key pain points. Firstly, connectivity, which means ensuring the seamless integration between devices, networks, and enterprise systems for real-time and remote visibility of the operations. Our partners want to expand upon existing motor management capabilities and gather data with ease without compromising on cybersecurity. We also want to help our partners design operationally efficient systems. We'll show how to connect motor management systems to streamline maintenance with clear diagnostic and strategic spares, whilst using historical trends to fine-tune schedules and set points. We'll also demonstrate predictive analytics and how that can help surface issues early, and how aligning control to demand actually translates into energy savings and lower operational costs. Many installations run in the punishing Australian conditions: flooding, heat, humidity, dust and salt air, to say the least. So reliability starts with selecting the right hardware that's built for the specific environment. We'll discuss how system design can be optimized for specific environmental conditions unique to each project. We've just talked about the importance of connectivity and gathering data using our connected products. Cherise, what kinds of data are critical?
Thanks, Haihi. So I guess first up, we've got 6 things on the screen here, and I'd say that the most important thing would be current and your voltage, because they can tell us a lot of different things. For instance, if you have winding issues, they may show up as like a current phase imbalance. So instead of one phase, 2 and 3 all being approximately equal, one of those phases may drop out. If a load becomes harder to turn, you may also see an increase in current, which can indicate something is jammed or some kind of overload on the process. And with your frequency you're running at, this might also potentially have an impact on the insulation class you select for your motor. And then with your insulation class, it's going to play a part in whether your motor's thermal state is within its limits. Dan, how about things like the contactor life cycle and harmonics?
Yeah, thanks for that, Cherise. So with obviously the ones that we're talking about earlier, current and voltage, they apply to both VSDs and to DOL systems. But if we move more to a DOL, then we're going to have contactors, obviously, to bring our loads in and bring our loads out again. And contactor lifecycle is just a byproduct of things having a finite life. The actual contact points within the contactor, where you get the little tiny, usually it's separate, different type of material where it actually bounces down onto the thing, but it does bounce. There is a degree of chatter, even though we'd like that to be 0, it's never going to be that way. And so every time that chatters, there's arcing. every time there's arcing, that is eroding those surfaces. So the contactors are rated for a certain number of cycles at their rated current or whatever their voltage is as well. So we need to keep track of that. The longer our contactor has gone on and the longer it is into its life cycle, we're going to run up against the bathtub curve. So towards the end of the bathtub curves where failures will start to happen. So it's good to know how many contactor cycles we've done compared to its actual rated life cycle, and then we can bring that up as a warning. I mean, the other one is harmonics. Harmonics tend not to, I guess, manifest themselves on the motor itself, but they clearly manifest themselves in the rest of the system upstream, but they can also have an effect on other bits of equipment around the drive. So if we've got sensitive communication cables and stuff, ideally they'd be shielded and in another conduit entirely, but sometimes they're not. And they can play with other devices, particularly other digital devices that have maybe low energizing current, things like that, where they can introduce those harmonics. And it's going to depend on the site somewhat as well and the grounding scenario. The other thing that we get is thermal states of our equipment. So whether that's actually the VSD or whether it's the motor. If we're talking about the VSD, we have IGBTs in there in the VSD, and those IGBTs will heat up because they're not perfect from an efficiency perspective. So the harder we drive that VSD, the more they're going to heat up. And at the same time, if we've got lots and lots of starts and we're driving our motor really, really hard from a load perspective, it is actually going to heat up internally. Its windings are not 100% efficient. So the electricity going in there, while it produces kinetic energy, there is also the side effect of having thermal energy that's produced. So it's good to keep track of those as well. Now, the drives are really good at that these days, particularly the more advanced VSDs will not just model what it thinks the motor thermal state's going to be based on its thermal mass, size, number of starts, current, and all the other things, but they typically have temperature probes like PTC resistors built into the windings, and we measure those, and we can have a look at the thermal state of the motor. That data is really, really important because one of the biggest problems that you see is that in hot areas or harsh environments, these motors fail or the drives fail, and it's usually just because of a thermal overload or they go into a trip state. There's so many factories that I've seen where they're like, oh, we keep getting trips on our VSDs at this time of day during these months of the year. It's like, well, it's very obvious that you have a thermal problem, particularly when you go back and look at the fault log in the drive and it tells you there's a thermal problem there. So that would tell you that you probably need to have better cooling or more ventilation in that cabinet.
Thanks, Sharice. Thanks, Dan. Now we would like to explore what essentially is a connected product. So Dan, what is a connected product?
We're really talking about devices that are capable of talking on a digital network. So they're capable of transmitting usually and also receiving data. And if we have a network available to us on a device, then that gives us a whole bunch of different options. Not only can we control it better, but we can read more data out of it. So we can actually read real-time operational and diagnostic data. We can read fault logs. We can read reliability data, everything. So, I mean, there's a lot of different protocols that you'll hear thrown around. So maybe you've got Modbus TCP, Ethernet IP, Profinet, EtherCAT. What else do I get? You get IO-Link on sensors now. You will still have Modbus serial as well in certain instances and a few other networks. But really, these idea of connected devices allow us to bring information. Whether that's upstream or downstream, they give us an information flow. That can go straight up to our PLC or to our SCADA system. So if we go up to our PLC, we can take that data and use it to react real time. So maybe we've got a PID loop running in the PLC rather than in the VSD, and so therefore the PLC needs to react to the sensors that are coming through. Or we've got diagnostic data coming from a drive, and the PLC now needs to say, well, okay, I've got 4 pumps in a duty standby solution, and one of my pumps has gone out, so I need to go and activate another one, and simultaneously at the same time take that data, send it through to my apps analytics and services layer, which is where we would normally put our SCADA systems or our MES or historians, and alert the operator that one of my pumps has gone out. Maybe I've even got an automatic workflow generation system, so that if a pump actually goes out on certain error codes in my MES and ERP and my workflow system, it knows that that error code means that particular drive maintenance, maybe bearing problem, or maybe it's a blocked pump, and it can automatically issue a workflow order to get someone out on site to handle that.
Okay, thanks, Dan. It's very clear that having these connected products means that we get those insights real time and we can do something about it. But not everyone's system or project will require the same level of connectivity. So, Dan, what specific factors should you consider when choosing the right connected products?
Yeah, I mean, that's an interesting one that I get asked a lot. Like, obviously, I'm designing architectures with customers and end users all the time. So this is one of those, and it's not just within motor control, it's within all factors, but particularly in motor control, when we talk about our solutions, the first thing, they're going to be constraints. We have to be aware of whatever constraints we've got in front of us. So if we're using an existing control system like PLC, and then we're integrating another connected product downstream of it, we need to be aware of what that system is capable of talking. I mean, it's very rare that you would find an automation system that can talk Modbus, TCP, Ethernet IP, Profinet, EtherCAT all at the same time. So you don't get every option available to you. You might have a constraint that, okay, maybe my particular one is talking Ethernet IP, and I have only copper available to me, so I don't have fiber. So now I've got a restriction on my topology. I've got a restriction on the network I'm actually using. Then I also need to figure out, what type of application is this? Is this an application that demands lots of diagnostic data, or am I after just a little bit? Maybe I just care about the thermal state and maybe the current and voltage and nothing else from that point, because it's just a really small machine. But if I'm talking about a really large pumping scenario, or a really large fan, like a cooling fan on a power station, a lot of those are DOLs, not VSDs, but because they're so critical and they've got these huge contactors on them for huge loads, we need to worry about contactor cycle, contactor lifetime for something like that. So it really does depend on the application, as well as the physical and logical network constraints that we've got in front of us.
Thanks, Dan. We have found a study that shows one of the most important aspects of digital motor management systems with regards to meeting sustainability goals is predictive maintenance, real-time energy monitoring, and automated fault detection and isolation. Dan has touched upon this in the previous slides, but let's explore a little bit more about what it means to gather all that data that we've got with the connected products and how to utilize this to achieve this business outcomes, as well as achieve some of our sustainability objectives. So, Charisse, now that we know how critical it is to have sustainably designed systems, what type of design and considerations should you be taking into account when creating your system?
I feel like to design something that is sustainable, you need to consider the life cycle and continued maintainability of that system at hand. So one thing with this is to balance the number of spares being kept on site, and looking to implement a system whereby you can keep a minimum number of spares to suit a maximum number of applications on site. An example could be around keeping a higher power rated product in a particular frame size so that it can be used for a few different applications if needed. You can also look at things like modular products, where only modules need to be replaced and not entire products.
Thanks, Charisse. That's a great point about keeping very strategic spares. How do we now use the data collected that we talked about earlier from our connected products to make better business as well as process decisions?
This can get passed up to that apps and analytics layer that Dan was showing in the previous slide. A good example of this would be, say, a pump efficiency function. So data-driven optimization would mean that over a few months of operating, the system looks at how efficiently your pumps, or how the efficiency of your pumps vary over time. And this will allow you to alter your operations accordingly. So by collecting the running data throughout the year, you might be able to adjust the way that you're running depending on the season. And that's data-driven optimization.
Thanks, Charisse. Beyond what you just mentioned, are there any other data that's useful for the operations of a business?
So, as we discussed before, like our motor management products are great at collecting a bunch of data for us, and things we're seeing more and more of are things like predictive maintenance, so real-time energy monitoring and automated fault detection and isolation. An example here would be something like monitoring of your contactors. So you can look at how many times it's opened and closed and how long it takes to open and close each time, and how this is changing over time so that you can again make decisions on replacements. You can also look at the efficiency point of your pump and how it degrades as the same pressures and flows are put through it over time. Things like this can indicate buildups in a pump or that you've got failing bearings, and that might point you to run your scheduled maintenance a little bit early to get the most out of your equipment and to reduce downtime.
Thanks, Charisse. It's great to see how there's so many different ways that we can achieve various sustainability goals, make our systems more efficient. We've talked a lot about the machine and the processes, but Dan, could you talk through how sustainably designed systems can also factor in the human element, and how we can design better, taking humans into consideration?
Yeah, no worries. Like, I mean, regardless of how intelligent all our devices are and how good our connected products are, they're still part of some form of installation. That installation is still ultimately going to be managed by people, and people are still going to have to do things on site. So we really do have to make sure that the human factor is accounted for here and has a bearing on how we design this, how we build it, and how we operate it. So, an example of the sustainably designed things that Sheree talked about before is modular. So at this point, we need to consider the human factor and say, how easy is it to actually do that modularity? And are we designing products that help in that case? So, maybe it's a contactor, like a high-powered contactor that has replaceable contact blocks rather than the entire contactor itself. But then we've got to think about, well, if I do that, how easy is that going to be to pull off? Can I design the product so it's actually easy to leave the main base part in place and then just replace the contact blocks? Or do I actually have to go in and replace the entire thing? So ideally, we're in the former. The other one is, standardized spares. One of the really nice things about making sure that we have standardized spares and fewer part numbers on the shelf is that there's actually a lot less training. So we can have people that are trained on a smaller number of bits of equipment, and they are better at and more familiar with those bits of equipment, so that when we come to an actual downtime event, we're going to have a much faster mean time to repair, because they're so familiar with, this is the only type of drive that I have to replace. I've only got to be familiar with the operational requirements of this one and how to pull it in and out and how to connect it all up. And I get so used to it that the wiring diagram, while I still have it in front of me, I'm already familiar with it. I don't need to constantly check it. And so being able to reduce that time to repair is really critical for a lot of these installations as well. The other thing about sustainability, and it's not, I guess, so much of a human factor, but if we do sustainability-based design, we're ultimately going to end up designing things that are more efficient anyway, and we use less energy overall.
Thanks, Dan. And we know simplicity is so critical in this complex world.
Yeah, it absolutely is. Like, we really have to reduce the load on the minds of the people on site or wherever this installation is. The less they're thinking about in regards to all these other things that don't matter that much, the more they can concentrate on the task. Humans are really good at problem solving and doing certain things, but they aren't that great at multitasking ultimately. So giving them a clear path to get something done is going to make that a lot easier, a lot simpler, and a lot more effective.
Thanks, Dan. And speaking of this complicated world that we live in, another thing to consider is that we live in Australia, where the conditions can vary drastically between state to state and region to region. And each region poses quite tough environmental considerations. So, Charisse, what kind of factors might we encounter living in Australia, and what kind of solutions out there in the market that can help us manage all of these situations?
Well, hi, as you know, we spent last week in regional Queensland, and if anybody knows, it was second week of March. That was a crazy weather situation. We had flooding, river crossings, proper four-wheel drive situations, and we're getting calls from customers saying that small pump sheds had been flooded. So all of these drives and direct online starters, they go through the ringer when it comes to Australian conditions. So when it comes to what we're dealing with in Australia, got a couple things on the screen. When we have a look at the factors, ones that pop out to me are definitely things like mechanical, chemical, and thermal stresses. So in these environments, you can look for particular conformal coatings on your equipment. So things like 3S3 and 3C3 are there to help protect against harsh chemicals and pollutants, as well as high vibration and high dust levels. You can also look to ensure that you have sized any enclosures correctly and that you've included cooling solutions where relevant, because you've got different environments depending on if you're working in underground environments, above ground environments, and then what sort of enclosures or housing you've got over your equipment.
It's great to hear that we have various solutions that can tackle all these sort of environments. So let's really zero in onto one case study. We have a Bundaberg-based recycling plant. We've got Dan who actually worked on this project. Dan, could you talk a little bit more about this project, specifically what happened before and how the customer has taken some steps to make some improvements?
Yeah, no worries. Thanks, Haihe. So in this particular case, it's obviously out in the Bundaberg region, recycling plant, lots and lots of conveyors and some big trommels to kind of rotate and sort out the different pieces of rubbish that go through, so they can sort it all to glass or paper or the different recyclables or non-recyclables as well. Now, the picture that you got there is what the end result is. The one beforehand didn't look anywhere near as nice and wasn't connected. So basically we had a few drives. We've got more drives in the new solution, but in the old solution, almost everything was DOL, and it was just basic motor circuit breaker, contactor overload. Not smart, not intelligent, purely hardwired for everything. And so, you know, that place ran, they got a fair few jams, they got, you know, things kind of, the overload would trip, no real reason why. Maybe it's not jammed up or anything like that. They'd reset it, it'd go back into operation kind of and they're okay with that. But they realized that they wanted to retrofit it because the old solution just wasn't maintainable anymore. They couldn't get some of the parts and things like that. So it was due for a refit. So the refit went through, and as you can see there, we've got a whole bunch of variable speed drives. Are actually more in another cabinet, but in that cabinet there's 8 variable speed drives on the left there, and then there's a whole bunch of these connected DOLs. So that particular solution there is called Tessus Island, and it is a connected DOL in that each DOL has current monitoring on board and intelligence. So not only can this thing turn on and off the motor, but it can actually check the current, it can check for phase imbalances, it can check for a few other things, and it models the thermal state of the motor as well. So what they found was that we installed this, commissioned it and everything, and it kept throwing up errors on some of the motors, and we were a bit puzzled because, you know, that didn't happen before. But what it actually turned out was a lot of these motors had real issues, like they had shorted windings or they had degraded insulation and stuff like that. And it was actually that the connected products were picking these up because these things had more intelligence in them. They're looking for real errors and found real errors, which were just never transparent before at all. There was just no visibility into the problems that were occurring. So some of these motors need to be replaced, some of them need to be serviced, and a whole bunch of other things. Once that was done, then, you know, the connected products are okay with that, and they're perfectly fine to run the motor, and they still collect data about any operational data, but they work, and the motors work. And as a result of that, we've had heaps less downtime on site from what happened, particularly nuisance tripping, because now the actual system tells us what the problem is, rather than just an overload going off and you go, well, I don't know why it tripped. Actually, hang on a second, I've got a phase imbalance here. I'm 40% down on one of my phases, or I'm 20% up on one phase compared to the other two, so there's a short in the winding. Or the VSD will tell you that it's actually got problems, because the VSDs have a whole bunch more diagnostics than the DOLs do. Or they actually have timers in there, even on the DOLs, to say my current spike that I would normally get during operation is going on for too long, so I've got a jam before I've even started. And it's much more intelligent to tell you what's actually going on.
Thanks, Dan. That's a great example of how using these connected products has really unveiled some very apparent issues that were otherwise unseen. But we have been talking a little bit about sustainability. Do you know any environmental or sustainability-related impacts that having these connected products as well as efficient systems has brought to light?
Yeah, well, on this particular site, one of the other things that we found is because everything there is collecting data about its energy usage, we can actually trend that and we can benchmark it. So we measure how much actual incoming tonnage there is in the trucks that go in, and we measure how much energy is being used to process it. So we can start to create benchmarks and start to create trending about how much energy it costs per ton. And that's really important because obviously electricity prices are always going up. They probably never will go down, but they're always going up. And so the council has a duty and responsibility to make sure that they're using their energy efficiently. And this system allows them to look at the operational and benchmark it even on days. So maybe they find that, earlier in the week, they get a more efficient kilowatt hour per ton of rubbish or ton of recyclable material, and compared to the rest of the week. And so they can actually look into operationally what's happening, and maybe there's a really good explanation for that.
Thanks, Dan, for illustrating this great example of our connected products as well as sustainably designed systems. I'd be very curious to know your thoughts on where you see motor management heading towards in the future and how we can look to and leverage this in the near future.
Yeah, so there's a lot of trends that we're going to see going forward. I mean, some of these are not just specific to motor control, they're specific to automation in general. We're going to see more and more cybersecurity. With the CRA Act coming into effect in 2027 for Europe and the EU, regardless of whether we like it or not, we're going to see an increase in cybersecurity. We're going to see more dependence on encryption. We're going to see TLS becoming more commonplace, certificates in use across the system itself. We're going to see device hardening, probably more complex password generation, role-based access controls, things like that. And that has a big effect on a lot of the things, particularly the more advanced products like the bigger VSDs and even some of the smaller ones, because they've typically got a web server on board them now for data collection and diagnostics, which is great, but conversely, that has an impact on how we implement CRA with that, which is the Cybersecurity Resiliency Act that's coming into play. The other one that we're going to see a lot of is AI at the edge. So obviously we can do AI models and train them in the cloud, and that's really good because we have all this computing power available to us now thanks to all the data centers. But ideally, we don't want to have reliance on the cloud all the time. So it'd be nice to have some of that calculation done at the edge. And as we see more microprocessors and more microcontrollers having the ability to run neural nets and some of the AI models themselves, we might train something in the cloud, but then deploy it locally. So the actual processing for that data is done at the edge. So we will see things like drives that have predictive analytics built into them, which is based on AI models that were trained from thousands of data points across the globe, but the calculation output from that model is now being implemented inside the device itself at the edge. And I guess the last thing that we're going to see, particularly for motor control, is the rise of silicon carbide. That's our next frontier for most of the VSD manufacturers, is to implement silicon carbide, because it allows us to reduce our operational losses drastically when it comes to heat. So when we talk about normal IGBTs in a drive, which is the actual component which switches the voltage into the motor and out, normally there's a time between when you turn it on and when it actually gets to its voltage point. And in that, the longer that time is, all that energy is basically lost as heat for the most part. So there's a huge heat factor that comes in. So if we can reduce that switching time, we reduce the amount of heat that's given off by those components, which means we can make heat sinks smaller, we can make smaller, they have less cooling requirements, all these other things that go along with it. And so silicon carbide allows us to drastically reduce that switching time and therefore make our drives way more efficient. We've got to combine that with things like active front ends and to reduce our harmonics. But because the drives get smaller, we can start to put some of those componentries and some of those systems inside the drive and take up that place. So we're going to get smaller, lighter, more efficient devices. And in certain circumstances, we're also going to get devices that have lower harmonics, which means we've got lower implications on the rest of the system at hand as well.
Thanks, Dan. We're very much looking forward to seeing these new technologies in the near future. Before we close, I'd like to share one key takeaway for anyone looking for a next step. We observed in a recently conducted survey that the key to success is also choosing the right suppliers with the necessary capabilities. This means choosing proven technical expertise to get these specifications right for the first time. True lifecycle support from design, commissioning, to strategic spares, remote diagnostics, and upgrades, as well as interoperability across your install base and ecosystem so that the motor control island that you've got connects clearly and cleanly to your PLC, SCADA systems, and enterprise systems. As Australian standards change around sustainability for businesses, so does the need for credible sustainability credentials and experience from your partners that translate into measurable energy savings and easy reporting of outcomes. So choosing the right partner is thus as critical as choosing the right equipment, because what you really need in the end is end-to-end capability that goes way beyond the motor control spectrum, and it also underpins your operation for years. So, we hope this webinar has sparked some interest in your discovering of the world of intelligent motor management, and we hope this journey doesn't end here and continues on.
Thank you, Haihe, Cherise, and Daniel, for such an engaging discussion. Well, now it's our audience's turn to get involved. So a big hello to everyone watching live today. Please make sure that you're sending through your questions via the chat box, and don't forget to let me know who your question is directed to. We have received quite a few questions that have come through both live and with registration. So what I might do is I'll kick off with some of the live questions. So big thank you to everyone. Now, the first person has sent through a question, and don't forget to actually put your name down to everyone. Like sometimes your tags, I'm not quite sure how to pronounce them. But we had a question come through, and I might direct it to you, Dan, if that's okay. And
Yep,
the
no
last
worries.
question was, is there more work involved from an engineer's end when adopting to these newer technologies?
I guess to some degree there can be on your first crack at it. Like obviously anything new, if you're doing the commissioning, if you're doing the design and installation, there's going to be at least some factor of you haven't done it before. That's okay. There's nothing wrong with that. But once you've had one go at it, you'll find that it's easier to be more templatized. So, in terms of the commissioning aspect of it, it's not really that different in terms of you're still going to get a drive to talk to a motor, or you're still going to get a DOL to do it. You're still going to have to tune the current settings, voltage settings, thermal settings, all those things. When it comes to putting the newer technologies in, it's not so much about that initial operation perspective. It's more around what do you want to do with the data? That's the real difference that comes out here. How do you want to contextualize that data that you can collect now? How do you want to turn it into an operational output? Because unless you're doing that, then having some of these new devices probably isn't going to provide that much of a value to you. It's still nice to have, but it's really about taking data and turning it into operational improvements. Because if you can't measure something, then you can't really improve it.
Awesome. Thanks, Dan. Well, funny enough, Dan, one of the questions that we had that came through with registration from Hassan, probably on this type of topic of how engineers can prepare for this technology. His question was more around how can they, I suppose, become an expert in this area. So, what areas should I be focusing on? So any advice that you'd give to Hassan would be welcome.
Yeah, so for a question like that, it's a really broad one, just because motor control itself is such a broad topic. So let's take the case of a VSD, for example. In my mind, VSDs are the intersection of power electronics, communications, and automation, because we've got high frequency PWM going out to motors at potentially higher voltages. We have to manage communications, internal networks, even within the drive itself, then to the outside world. Then automation in terms of how do we run those motor control algorithms with things like flux vector control instead of the normal Vita Hertz that we used to run. And then are we running closed loop systems? Are we running PID internally in there? There's just so many different things that go on inside a drive now, as a quick example. So in terms of an expert, it's going to depend what part of that system you want to be an expert in. Do you want to be an expert in motor theory? Do you want to be an expert in power electronics, signal analysis, application knowledge, communications buses, even just data analysis from the perspective of that operational data that you pull up into the higher levels of your automation system? Which part of that do you want to be an expert in? Because they're all different skill sets to some degree. It'd be hard to be a really focused expert in just one of those. I mean, motor theory and power electronics, it's probably going to be university to some degree with electrical engineering. Same with signal analysis. Application knowledge and commissioning, that's really down to experience. That's being out there commissioning thousands of motors for the most part. Communications buses, there's a lot of research you can do outside of a place like university. It's probably good to do some basic networking stuff. But if you want to be an expert on, CAN, serial, Ethernet-based topologies, depending on the protocol, are you talking Ethernet IP, Modbus TCP, Profinet, EtherCAT, all those stuff? They require different types of research to be an expert at it. But again, a lot of that still comes down to experience. If you really want to be good in any aspect of motor control, experience is probably the major thing. I know guys that have been in the industry for a long time. They never went to university for any of that stuff, but they are experts in their field because they've basically seen everything and seen everything go wrong and know how to avoid that.
Awesome. Thank you. We had a question come through from someone, Avenging Moth, who is just had to say great session to you all. So thank you, team, he said, or she. The question is, keen to understand more about how the motor pump health diagnostics integrate with other systems like Aviva Prism. So I'm thinking I might direct that one to you, Dan.
Okay. Yeah, so motor and pump health diagnostics, it's going to depend somewhat on what your system upstream is actually looking for. So if you've got a system that's classifying fault codes and classifying faults and then therefore generating work orders or specific alarm information stuff, all that stuff is easily passed up. Like you might use Ethernet IP to talk from your VSD, which now the VSD has a lot of that edge processing internally. So it handles the VSD and the pump as kind of one aspect. It has inputs that you could put your flow pressure sensors on it. So it can now generate its efficiency based on the pump curve that you also input into the drive. And its diagnostics about run hours, flow throughput, any reduction in flow over time or reduction in efficiency over time. All that information might go up on Ethernet IP to your PLC or automation system or DCS. And then that may go up on something like OPC UA, I don't know, up to your Aviva system or up to some other higher level system. It's going to depend a lot on your site. So, I see a lot of water treatment sites where because they've got the intelligence in the drive now, they get to benchmark their pumps. So they know that these 5 pumps in this same region should operate the same way. But if they start seeing one of those diverge from the other 4, then there's an issue somewhere. It's probably going to be a block pipe or there's a bearing going wrong or something like that. And quite often the drive itself is capable of giving you an insight as to what that might be. We're now seeing, I know that we're about to come out with a system that is looking at the current and voltage waveforms that come from the output of the drive that go to the motor, and looking also at the harmonics that come back from it. Because remember, when you're sending these high frequency pulses, which is how a drive works, it can't actually synthesize a true sinusoidal waveform. So it does duty cycle manipulation of a voltage source, which then combined with the capacitance and the inductance in the coils of the motor and the windings, as well as the cables going out to it, produce a pseudo sine wave at that point. Now we're using some of that information along with some machine learning trained data to actually classify different faults. Like if we're seeing a rising ground current leaking out of the motor, there's a good chance some of that's coming from the bearings. Or if we're seeing a particular harmonic be more prevalent than it was over time, then that would indicate other particular problems within the drive, like certain types of insulation breakdown, stuff like that. So you can integrate it all. It's really going to depend on a site-by-site basis, but all the information now is there. It's not a case of you going, oh, I wonder whether I can measure it. It's not whether I can measure it, is do I want to use it?
Awesome. Thanks, Dan. The next couple of questions have come through, and they're probably more around the client, the operator. So the first one came through from, I think, Simon Ellis. So big hello, Simon, watching live. What steps do you take to ensure your client operator is ready for an aspect of operational transformation? For example, support for a digital product as opposed to a conventional lights and buttons approach, which I think is a really good question. Maybe Dan? Anyone else, please let me know if you want to jump in.
What steps do you take to ensure your client operator is ready for an aspect of operational transformation? Again, the human factor is always going to be one of the biggest things here. No matter how much technology we might want to jam in there and how much smarts the device has, we still have to ultimately be able to play with the people. So to incorporate ensure your client is ready for the aspect of that. Probably the main thing is it's going to be sitting down with that client and really understanding what their challenges are on a day-to-day basis. Once you know what their challenges are on a day-to-day basis, you can then look to the intelligent connected product and say, does certain features of this allow me to solve those? Because once people see that certain things they had to think about all the time before, they now don't have to think about, and it's not a problem and the system will take care of it, they're much more open to actually employing some of these things. So in the case I just talked, the case study for the Bundaberg recycling plant, they had lots of nuisance tripping, didn't know what it was. But the moment we can show them that we can now measure what the problems are and classify those problems and allow them to fault find them so much quicker, because if you know you've got a phase fault, that's way better than running around trying to figure out, well, why does this motor keep jamming? I'm going to have to go take everything out of service. The intelligent device is actually telling you what the problem is, so you can go and either order a new motor or order a motor rewind without having to spend days figuring it out. So it's really, again, about what is the client or the operator's pain points, and how do we classify the things that these intelligent connected devices actually do to deliver solutions based on those pain points.
Good advice. Definitely work on the things that are hurting them and try to fix them. So great advice.
And
Dan.
people are always much more welcome to putting in new technology if it's going to actually solve a problem that they had.
Yeah, definitely. Well, hi, we had a question which came in from Adam, and Adam has asked, clients can be reluctant to employ smart systems that limit interchangeability. Are there suggestions how to incorporate recent device smarts without locking into a proprietary system?
Yeah, for sure. I think that is a struggle that a lot of the engineers and partners that we work with face, because they have a certain preference of PLC that they're used to using. And it's not just about the devices too, it's also about the people and their training. They might be quite keen on one specific brand because they're an expert in that area, and then incorporating smarts that they found in another brand might not really work well. So we look to products that do have the ability to interoperably work with other, no matter what sort of comms you have or other devices that you have upstream or downstream. I can speak to us at Schneider that we like to create devices taking into account people's existing situations. For instance, we don't just develop for one sort of comms communication type. We make sure we take into consideration what there is in the market out there, because we understand uprooting everything and changing out the entire control system is not really a feasible task. So we do try to have and continue to develop products that have more interoperable softwares and systems at play. And then we acknowledge the reality of the situation that even though we want everything to be in one brand, it's not always going to be the case. And I think that's a key benefit to those people who are looking to incorporate more smarts into their system, like one step at a time, as opposed to creating a huge greenfield project and incorporating it all in one go.
Awesome, thank you. We had a question which came through from Nazmul. For brownfield work, where an already running system is built from multiple manufacturers, how adaptable this system is to coordinate with the present system? Hopefully I've explained that well. So I think it's built from multiple manufacturers, how adaptable the system is to coordinate with the current system. I think I might hand that to Dan.
Yeah, no worries. Yeah, well, there's nothing wrong with that. Like, that's how brownfield systems work, when they're kind of pieced together at that point. What really matters here is that, can your current system handle some of the more common protocols? You know, we would typically see Modbus TCP, Ethernet IP from our perspective as being the normal ones that we use. We can do Modbus serial as well. But just also remember that just because you've got an intelligent device doesn't mean it cannot be controlled with standard digital I/O. So I might have a VSD with all this incredible processing power. Do I have one here? Oh, I do actually. Hang on. So I might have a little VSD here, like a machine one, and it's got heaps of I/O on there. So I can actually use that I/O to talk to my existing brownfield system. But at the same time, that device is capable of generating more data over a communications network. So as long as I have communications infrastructure on site, I can take the operational data from it that is not to do with the control and basic monitoring of it, like more extensive operational data, up into a system that sits on top of that brownfield. So, you know, I might have a bigger SCADA system, or I might have an asset management system where I can actually take the operational data from here and treat it as an asset. And that's irrespective of what my downstream system does. I still may just be using relay outputs, analog inputs and outputs to control this and monitor it on my brownfield to give you interoperability for an older system, but then use the Ethernet available data to give me operational insights that I didn't have before and make, you know, real change and real effects on how we operate the system. Hopefully that answers a little bit of that.
Thanks, Dan. We had a question which came through, another live one on PPP projects. If availability payments are increasingly driven by data, sensors, and platforms, how do we ensure that a failure of the monitoring system itself doesn't incorrectly trigger abatements? Can I hand that one to Dan?
Yeah, okay. That is that's a big deal. You can't rely on a single source of truth for everything at that point. You want to have, if it's that important for your project that all your availability payments are increasingly done by that, then you're going to have some form of redundancy in there, or some form of multivariable monitoring to ensure that you get some quality in your data. So maybe on my VSD, I don't just rely on how fast it's running the motor because you can do flow estimation on pumps now. Would I trust that for something that requires availability payments? Probably not. I'm probably going to have a flow sensor with a pressure sensor as well on the pump, so I'm actually getting some verification of that data. And I might have an AI model over the top of that, over my system, that actually says, look, is the data I'm getting from my flow and my temp and my pressure sensor and how fast I'm running the pump and how much energy that pump is consuming, is that all congruent with the operation of my plant? Because if suddenly I'm supposed to be running at 45 hertz, but my flow is way down and my pressure is way down, there could be an issue there. Maybe there's actually a blown pipe or something like that. But it also could be a sensing issue. So you want to have that. You're going to have a zone where your measurements do coincide with each other and they don't tell the wrong story of the truth. If that might, they're not lying. You do want to have some form of. It doesn't even really need to be redundancy so much, but you want some cross-checking across measurements to ensure that you're actually in a zone in your readings and where your calculations are that make sense. Because if your data doesn't make sense, then you can't trust it and you can't use it for the rest of your failure prediction. And AI is really good with that one because at that point, we're using anomaly detection. Anomaly detection is great to specify bounds where my data, with these congruent readings of different things, they should all add up to this, or there's some form of a nonlinear equation that relates them within a zone. If it falls outside of that zone with the numbers, then I have a problem and I do need to investigate what that is.
Okay, I've got a question for you. For smaller motors with conventional starters and VSDs controlled via PLC, DCS, and a process plant, is there much value in having an integrated motor management system given the additional cost?
I think that's a great question because all of the things that we've been talking about does have a level of investment at the start. And especially if it's a fairly simple system that is already working, 80, 90% of the time, it might be easy to go, like the cost is not worth the potential benefits that we might see. I work in the motor control DOL space, so I'll speak to that as an example. And a lot of our partners that we work with, or engineers, or electricians and contractors, they can be a bit skeptical about this initial upfront cost. That's why, again, speaking to Schneider, we want to, again, acknowledge the reality of the situation that people have complex needs sometimes, and there are also people with a little bit more basic or simple or more straightforward requirements. In those circumstances, we do have different solutions that we would provide and offer. So let's say we actually did have a very standard basic direct online system with the contactor, the overload, the breaker, and they're not really necessarily talking to each other. A more critical mine site, for instance, might go the full hog and have a intelligent motor control system. But if it's for a less critical application, let's say, but we still want to know and predict and understand what's going on with our system, we can still also get smart DOLs or smart direct onlines that can actually monitor the current information, for instance, so that we do get an elevated level of understanding of what's going on with my system and still be able to track the trend of what the motor performance is without necessarily going through and having a huge investment from a CapEx standpoint. One thing to note is even if we do have a bit of an investment at the start from a CapEx angle, the savings from an OpEx angle can be quite immeasurable, and it's hard to calculate if that calculation has never been done before. So I would definitely recommend exploring the different types of solutions that are out there, not just it's not just a black and white or like no connectivity versus 100% connectivity. We'd have solutions that fit every different type of unique project. And I think that's something that I would encourage exploring more. And I think from a cost perspective, it doesn't actually end up becoming too much compared to an existing DOL system, especially if you take into consideration the installation costs, the programming cost, and the operational benefits that you see in the long run.
Thanks, Haihe. We had a question which came through from an audience member based in Asia. Which method of motor control is preferred in view of ease of troubleshooting and system maintenance? Is it hardwired or communications? I might hand that one to Dan. And we are getting to, I think we're pretty much nearly at the end of the Q&A today, but Dan, I'll do that one for you.
Okay. So method of motor control preferred. It's a little bit of a misnomer because if we say method of motor control, in my mind, that's talking about the actual motor control algorithm we run on the motor. So whether it's V to Hertz mode, whether it's closed loop, whether it's flux vector control, a bunch of those other things. But I understand where the question's going. They want to know, is a hardwired or a comm system easier to troubleshoot and maintain? And the answer is going to depend entirely on the site. I mean, if you already have communications in place, they're already geared up for that. So that's not really a big deal. What hardwired sounds nice because it's simple. It's either working or it's not working. And sometimes the drive may have a screen on it so that you can read the error codes and things like that, but you physically got to go out there to do it. What's nice about communications is when it comes to troubleshooting, as long as you've configured it properly, it can alert you back up in the control room what went wrong with a time and date stamp. So you can just look through your SCADA and go, oh, drive at 12:45 p.m. said that it had a thermal state shoot above 90%. That's a problem. And I can look back in the fault log and see that I also had a jam 20 minutes before that, and I had this other problem, and maybe I can relate that motor, the drive thermal state, to an internal cabinet temperature if you're monitoring that, and you can look and say, well, the internal cabinet temperature went beyond what it's supposed to, so of course my drive thermal state, which means that I'm not actually looking for a problem with the drive then, I'm looking for a problem with the cabinet. Because if you just look purely at the drive, you go, oh, the drive had a thermal problem, and then you go down this rabbit hole trying to figure out why the drive had a thermal problem without considering what the rest of the solution looks like and where potentially some of those fault sources might come from as well.
Awesome. Thank you. Well, look, I think the final question that I might direct to each of you is any final comments or key takeaways that you would like to leave with the audience today? And I might start with you, Haihe.
Thanks for the question, and I think it's a really good one. And just want to put on like a sustainability lens just for a little bit. I know, like in Australia, sustainability is becoming a more and more important topic, and especially like government mandated reporting and things like that. It's becoming more and more prevalent. I really commend everyone for joining this call because we're talking about intelligent motor control, which may not have an obvious link to sustainability and sustainability reporting, but motors being 45% of the electricity usage around the world, potentially more depending on what industry you're from. Being able to use these types of devices, consider these more intelligent systems, I think will definitely put a lot of companies and partners and end users ahead of the curve. So I really commend everyone for joining this call. And I would look to intelligent motor control and intelligent motor management as almost like as a selling point / point of difference between those who don't have this level of smarts to those who do. So hopefully this can also pinpoint the inefficiencies that you have in your organization that you've never seen before. And we'd love to keep in touch and keep connected.
Great answer, Haihe. Dan, your final comments.
Yeah, I guess the biggest final comment I have is don't forget the human factor. We can throw technology around to the nth degree, but it's ultimately got to come down to how do you want to operate your site or your plant, and how do you want that technology to solve problems for people. It doesn't by itself just automatically solve a problem. There's got to be a need. There's got to be a problem to solve, and the technology has to play to that. And we want the technology to be another tool in the arsenal that controls engineers and operational engineers have on sites. We want it to be a value add, not a distraction that makes life difficult.
Thanks so much, Dan. And I think, unfortunately, poor Cherise has had some technical IT issues. So apologies that we're not able to throw to Cherise for her her final comments for today. But look, on behalf of the panel, I would like to say thank you to them all. So a big thank you to Cherise Taberner, Haihe Shin, and Daniel Hancock. for their really engaging presentation. Really appreciate that. I would also like to thank Engineers Australia's industry partner, Schneider Electric, for their support. Now, if I could ask on behalf of Engineers Australia, if you could complete the short feedback form, which is linked in the description box below. As you all know, that feedback, it really does help us to improve and plan future sessions for you, our audience. So, look, thank you all so much for joining us today, and we hope to see you at our next Industry Partners event. Good afternoon.